Hello and welcome to PC Retro Tech. In today's video I want to show something new I've been working on for a few months, some brand new graphical effects for vintage PCs. Now there's a bit of a battle on YouTube between creators who want to show something that the audience hasn't seen before that they did themselves, and others who just want easy views, maybe make a reaction video to whatever the latest trend is, like this UAP nonsense that's been in the news or something like that. But I've been working really hard over way too many weekends coding on this beautiful compact 386DX25 to my left here. It's a machine I featured on the channel, and when I built it I got so excited I immediately wanted to do some 256 color VGA graphics programming, and I've been working on that ever since. This machine has no math coprocessor, so no cheating there. I switched out the original compact VGA monitor for an NEC multisync. It's just a bit bigger and clearer, and it's hopefully going to give a better image for you guys. But at the same time I built this, I got really interested in old drawing programs from the 1980s and early 90s, and I made a video about this on the channel showing some of those. By the way, one of the really cool things I want to show today is another one of these programs pointed out by a viewer. But this is Jim Leonard, aka Trickster, a good friend of the channel, and frankly this is the sort of thing that only he would remember. It was like disc 344 in this massive old shareware collection, and I'd wager that more than 95% of us have not seen it before, and boy is it worth checking out. But the main thing I want to show today is this new code I've been writing for basically animating ellipses. Some of these early drawing programs could do horizontal ellipses with horizontal and vertical axes. But if you wanted to do something at a different angle or rotate the ellipse, then you needed what's known as a general ellipse or diagonal ellipse. And my goodness, does this turn out to be a difficult thing to implement. The internet was no help here whatsoever. I had to dig into the mathematical literature for algorithms. And yeah, they're just full of problems, as I'll show. So after many failed attempts and thousands of lines of assembly language, I finally have something fast enough and accurate enough to animate. So much so, I'm going to make some pretty bold claims. The first is I think it would be prohibitively difficult to do this on a 286 or earlier. Maybe not for the reasons you think, and I'll explain what I mean by that a little later. The other claim I'm going to make is if you used any of the cheating methods that some of these early programs used, you would end up with a lot of graphical artifacts on the screen and basically just a mess. And I'll try and show that in the video as well today. So this was a really interesting one, and hopefully you'll find it the same, especially if you like old PCs and graphics. So let's get stuck right in. Let's begin with lines because they're really simple and all the main ideas behind these algorithms already pop up here. So what we're trying to do is something called scan conversion, and this is where you've got a line or a curve or something like that, and you want to try and find pixels that as closely match it as possible. So just think of these squares, by the way, as being pixels on the screen. Actually they're usually not quite square in practice, but yeah, that's a story for another day. So this line is at 45 degrees and it starts at 0, 0 up here and goes down to I think 13, 13 here. So this pixel is 13 across in the X direction and it's 13 down in the Y direction. By the way, that's actually the opposite way that mathematicians do it. They actually have the Y-axis going up the screen instead of down, but yeah, this is computer graphics, so it has to be different, of course. But yeah, to scan convert this line is really easy. We start at 0, 0 and then go to 1, 1, 2, 2, and you can see that each time the X coordinate is going up by 1 and the Y coordinate is going up by 1. And that happens for lines at 45 degrees, and you end up with pixels that are bang on the line. Like the center of this pixel is literally on the line. And the other easy cases are where you have a horizontal line and a vertical line. I'm pretty sure you can see how to draw those. So the thing that's going to matter for us is the slope of the line. Now the slope is just how far you had to move in total in the vertical direction divided by how far you had to move in total in the horizontal direction. And in this case, we go down to 13, 13, so it's just 13 divided by 13, which is 1. So this line has a slope of 1. And the other easy cases are the horizontal line with a slope of 0, and actually the vertical line has a slope of infinity, I guess, because we had to divide by 0. So the only cases that are going to be difficult for us are other kinds of slopes in between. So here's an example that isn't 45 degrees anymore. It's a little bit more horizontal than it is vertical. And if I fill in a few pixels here, we'll be able to see what's going on. First of all, the pixels aren't exactly on the line anymore. Like the center of this pixel is right here, which is well below the line. And if I fill in the remaining pixels here, I'll explain exactly what the main idea is behind all of these algorithms. So this is maybe the most important idea. You can see that because this line is more horizontal than vertical, we always move across to the right every single time by exactly 1 pixel. So there are no cases where we don't do that. So in other words, we always know exactly what to do in the x direction. We just increment by 1 every single time. The only thing that really remains is to figure out when we should increment in the y direction. You can see that we don't always do that. I mean, all of these pixels have the same y coordinate, for example. And the way it works is that, for example, this pixel here is above the line. So it certainly doesn't make any sense to just keep going across to the right. We'll be even further above the line. So that's the point that we should go down by 1. But now we're a little bit below the line, and so it does make sense to go to the right. Now we're a little bit above the line again, so here we should go down. And you can see that all the times that we go down by 1 pixel are precisely the cases where we were above the line. And so the way this is handled in practice is using something called a decision variable. Basically, it tells you how far away from the line you are. So if the decision variable was positive, for example, you might be below the line, and if the decision variable is negative, you're above the line. And so you can use that as a guide to tell you when you should move down 1 pixel. So I've actually gone ahead and implemented a very famous line drawing algorithm called Bresenham's algorithm. And it's just a minor modification of what I've already explained. But I'm going to display the values that it uses internally down in the bottom left. Actually, when you're drawing straight lines, 2 of these don't change. They remain constant. The first one, dx, is just how far we have to move in total across in the x direction. So that's 25 in this case. And dy is how far we have to move down in the y direction in total. So this is the decision variable I was talking about here. Now you might think something's wrong here. This point is bang on the line, but the decision variable is not 0. And that's because this doesn't actually work very well for curves, and that's not how Bresenham's algorithm works either. If you had a curve, it could drift up a little bit and drift down a little bit and so on. And what really matters is not where you currently are with respect to the curve, but where you're going to be with respect to the curve when you move. And of course, you've got 2 choices always when you move. For example, here I could go to this pixel or to this pixel. So what Bresenham's algorithm does is it examines the point that's exactly between the 2, right in the middle, which is this point here. And you can see it's just a tiny bit below the line. And so that has a small negative decision value. And that's enough to tell us that we should move right. The next option is between this pixel and this one. Exactly halfway between them is here, and that's actually now above the line by quite a bit. So we should have a quite positive decision value, and that's our cue to move down a pixel. And again, choose between this and this. Here's halfway. It's below the line. We should have a negative decision variable. So negative means move to the right. Positive means move down. And that's all there is to it. Now, I'm not going to explain exactly how to compute the decision variable. You can look that up online. It's just some combination of these 2 values. And modulo a few small changes, that's basically how all these algorithms work. Already years ago I implemented this algorithm on my PC. You'll see it running here on my XT, but same thing, an 8088 CPU at 4.77 MHz, and 4-color CGA graphics, one of the options available with the original PC. Now you can see the file sizes are quite small here, under 1 kilobyte. This is done in assembly language, but it is a moderately sophisticated implementation that I've sped up over the years. The first version is just going to draw a line that's more horizontal than vertical. Not much to look at, but it gives you an idea. The second one will draw 2 lines, one that's more vertical than horizontal and a diagonal line. And the final version is going to draw lots of lines, and we'll be able to see how fast it goes. We get about 100 lines per second, and the fastest version I have could draw about 6 lines per frame and erase them if they were short enough. But this is not great for animation, and so you'd have to use other techniques like drawing the object off screen and copying it on when it's ready, and that might slow you down to about 20 frames a second. So that's what you can do on a PC. Now I'm going to show you an implementation using my compact 386, or 386 depending where you're from, and this is a major uplift. It's a 32-bit CPU and it has a higher number of instructions per clock, faster access to memory of course, and it's 25 MHz. In addition to that, I'm going to use a VGA card, and this is much faster than CGA. I'll also be doing 256 color mode. Unfortunately that does mean 70 Hz for the monitor instead of 60, and my camera doesn't do that. In fact, it can't even do half of that, so I'll have to film at about 23 frames a second. That means that you're going to get a kind of sluggish look on film, and it kind of defeats the purpose of doing things as fast as possible, since the camera can't keep up anyway. At any rate, you'll get the idea, and there's also going to be a kind of rolling shutter effect, but this is visible to the naked eye. But way fast enough for animation at least, and so I'm going to use this for as many of the remaining effects in the video as possible. Well, I thought I'd do just one simple line demonstration before moving on, and it's just going to bounce a line around on the screen, and don't adjust your television set. There are some pretty garish colours here. So this is obviously going very fast, and in fact every time it moves the line here I'm actually drawing 4 lines, so it really could go a lot faster still if I wanted to. Now funny thing is, when I first started doing VGA on this machine I got a blank screen, and it took me a while to figure out it was because EMM386 was turned on in my configsys file. And I didn't check, but from memory what this does is throws the processor into a different mode, and the actual instruction coding is different. So anyway, I fixed that, and now it's working just fine. By the way, here is the original line drawing algorithm by Bresenham from 1965. This is the IBM Systems Journal, and he actually developed the algorithm in 1962, and I bet you're wondering how on earth they drew things on a screen without modern graphics hardware back then. And well, of course this was an algorithm for a digital plotter. It says that the algorithm was designed to not use any multiplication or division instructions, and this is very important on early CPUs because those instructions were very expensive. Division still is to some degree. You can see the plotter could move in 8 different directions, and he discusses how if you are plotting a curve you could construct it out of short segments in those directions. So here's his discussion of the line, and you can see that as you plot the points that the plotter can actually reach, you go one side or other of the line. And yeah, the rest of it is pretty much just maths. There's a big table with his decision variables and the various cases that he had to deal with. That's basically it. So yeah, it's nice to look back on this history and see where all of this stuff came from. Well, it's time to take a look at a circle drawing algorithm, I think, and the one that everyone seems to use is the midpoint circle algorithm, and it's actually really similar to the line drawing one. But we've got a bit of a problem now. Remember with the lines, when we had a line that was more horizontal than vertical, we knew that we always had to increment the x-coordinate every iteration. That's clearly not going to work on a circle. But it does work for 1/8 of a circle. This octant here is always more horizontal than vertical. And we can just use the symmetry of the circle to get all the other points. So it's a little bit clearer if I put a few extra points in. you can see that this is the only point that I actually computed. The other 7 that just got added are just reflections about various axes. So we use the symmetry so that we only have to draw the 1/8 of a circle that's more horizontal than vertical. And other than that, it's pretty much the same algorithm. The only difference is that because the circle is curvy, we don't end up with just 3 variables internally now, but 5. So we still have a decision variable, and it's updated every time in terms of 2 other variables. And these actually change now. These are not constant like we had in the line, and that reflects the fact that the circle is curvy. So these themselves have to be recomputed every iteration, and that's done in terms of some constants down here. So these won't change every iteration, and that's all there is to it. The main reason for all the extra complexity here is because it's a little bit more difficult to figure out how far away from a circle you are than it is for a line. And so the maths is much more complicated, but the actual algorithm itself is really only a minor modification. So let's follow it through. It's telling us that we have a negative decision variable. That means we should move right, and that happens. Negative again. Now it's positive. We should expect it to move down 1 pixel, and it does. Negative is right, right, down, and you can see how it works. So yeah, we end up with a really nice scan-converted circle. Okay, I wrote a routine for doing circles in VGA, and I call it lots of times. Unfortunately, I had a small bug in my code, which meant that the circles ended up having negative radii. But the code keeps working anyway and does some interesting things, and I thought it looked good enough to actually show you the buggy version before I show you what I originally intended. So here it is, and I think it looks okay in the end. Sometimes this happens when you're coding. You make a mistake and the result ends up looking interesting anyway. Here's what I really intended. It draws a circle, makes it slightly smaller, and then changes the colour, and then repeats over and over. And actually, in order to slow it right down, I'm drawing the same circle essentially 9 different times before changing the size. Otherwise it just flashes too quickly. The other thing to bear in mind with circles is that the pixels aren't square on the monitor, so if you really want a circle, you actually have to draw an ellipse. And the ratio is something like 6:5, I think, in order to get the thing looking like an actual circle. So it's certainly plenty fast enough, and lines and circles are like that in assembly language on a 386. I think now is a good time to show this program that Jim Leonard found. It's called PC KeyDraw, and it's part of a collection called PC Sig. It is actually disk 344, and I'm running it here in an emulator that's online on the PCJ's machine's website. And there's a link in the description that'll take you directly to this program if you want to try it out for yourself. So I think it's KD Draw to get it running. And as far as I know, it's written in BASIC. I'm just going to skip over the setup screen here. It is compiled BASIC, if that. And it's not mouse driven. It has a menu system on the function keys. So F1 gives you rotation, zooming, and mirroring, flipping, video reversing, and sliding. I'm not going to show all the features here because it would just take hours. There's a box and figure menu. So let's draw a shaded box. So we'll draw something fairly small just in the interests of time. And that should do it. And we'll shade that in. So there are a few other options in there. There's polygons, arrows, and outline. And the F3 menu, this is the one we're interested in, curve draw. We have arcs, and first of all you'll draw a circle, and then depending on whether you go positive or negative, it will either subtract from or add to a circle, and you can basically just mark off the portion of a circle that you want to draw. So then there is a circle routine and an ellipse routine. Unfortunately, just horizontal ellipses.
but they look very nice. It's done very well. And this is an ellipse, as you might expect it to look. And next on the list is fillet, and that's just basically similar to the arc routine but for an ellipse. So I won't show that one. There's rose curves, so we'll do one of those. I have to make this one fairly large, otherwise it doesn't look very good. So let's do it this size, and I'm going to do 6 leaves, and I'll do a sine curve. So that's the rose. The next one is a spiral, and I don't want a very large radius here, about that will do. And I'm going to do just 4 spirals because it gets quite large quite quickly, as you can see. So you can have a lot of fun with this. Is there anything else on the curve menu? Oh yeah, the trig sine one. So let's select that one. And this one just draws a sine curve basically. Yeah, a lot of features there. And in addition to that, there's also a way of running this with a kind of presentation setup so that you can do slideshows and all sorts of graphics, animations and so on. And in addition to that, you can also run other programs from within PC Keydraw. So if it doesn't have the features that you want, you can just add them, or you can do other kind of batch scripts while this is running. So very, very powerful program and pretty much unparalleled at the time.
Well, we've done circles, it's time to do ellipses. And it turns out you can just modify the midpoint circle algorithm. An ellipse is just a squash circle. Unfortunately, it's really hard to find the implementation on the web because a lot of graphics courses teach the midpoint circle algorithm. There are hundreds of versions of that, but midpoint ellipse, there's only a handful, and a lot of them are wrong. So in the end, I designed my own algorithm for this. Now, there's a few changes you have to make. First of all, with an ellipse, you have a center point, and you need 2 radii instead of 1. You can see that not all the points are the same distance from the center. So I call them R for the horizontal radius and S for the vertical radius. And actually, those are the constants that end up being used in this algorithm, or rather the square of those values. The other change that you have to make is you don't have 8-way symmetry anymore, and so now you have to draw an entire quadrant of the ellipse. And the way this is normally done is to draw one octant, stop, and then restart here and draw another octant going up and meeting it in the same point. Now that can cause some problems when the meetup occurs, so my algorithm actually does first one octant, switches some values over and keeps going in the same direction. It just saves any issues with the meetup here. Now otherwise the algorithm's pretty much the same. These values will be updated by something like the square of these, and I'll leave you to figure out what the combinations actually are. And this will be updated by one or the other of these. And so let's see what happens when we run this. It's got a negative value here, and of course for the first octant we're always going to be moving south. The only decision is whether or not to move west as well. In other words, whether we want to do south or southwest. So at the moment it's negative, it's telling us to go south, south again. Now it's positive and we'll have to go southwest. And it'll keep going until it gets to the point where the slope is -1, and then it'll switch over to the next octant, and you'll see that happen here. This will change from ds to dw, and the reason for that is because for that portion of the ellipse we're always going to go west. The only decision is whether to go south as well, so it'll be d west and d southwest. So let's go until we reach that point. There it is. Now it's d west and southwest. And basically, if the decision variable is positive, it's going to go southwest. If the decision variable is negative, it's going to go west. And you get a nice scan converted ellipse. Now, one of the problems with this algorithm is these values are really big. We're updating these by about the square of those values.
And so these will end up being around about the cube of these values. And those are going to be huge, especially on a monitor where you can have many more pixels and where these radii could be much higher. And the problem with that is that these values will then overflow the 16-bit registers in the CPU. Now, it turns out that with one hell of a lot of fiddling around, you can actually get this algorithm to work with 3 24-bit values. And unfortunately, you still run out of registers on a PC and an XT. So what I had to do is sacrifice 4-way symmetry. It's just too much to keep track of, and if you do 2-way symmetry, then you can fit it all in registers. And you want to do that because writing out to memory instead of using registers is much slower on the PC. And so basically with just 2-way symmetry, it means you have to draw an entire half of the ellipse. But of course, I just use the same algorithm for that. I draw one quadrant using the algorithm I just showed you, and then I just switch it around a little bit to go in the opposite direction and draw the other quadrant. And the other half of the ellipse is done automatically with the 2-way symmetry. So let's see that in operation on my PC.
Here's a version of the ellipse code that I wrote for the PC a long while ago. So this is 16-bit code, but I'll run it on my 386 because it's only going to display a single ellipse. And as you can see, this was for 4-color CGA, and so I'm not going to bother animating this. You'll see a lot of animated ellipses later on. It's a pretty smooth result, and I tried to get it as close to pixel perfect as possible. That was very hard on a 16-bit machine, but after really quite a few weeks of trying, I was able to do that for pretty much all sizes of ellipse.
Well, how are we going to draw general or diagonal ellipses? It turns out there are multiple algorithms in the literature. The earliest I can find is just 2 years after Bresenham by Chataway, and that allows you to draw parabolas and hyperbole, basically other kinds of conic sections as well. The next one I find is Kappel's algorithm from 1985. He also had a paper in 1991, and I'm not going to talk about that because I don't know very much about that algorithm. There's also Da Silva's algorithm, a master's thesis from 1989, and that's actually the one that I'm going to implement in this video. It's the one that worked best for me. There's also a very recent algorithm by von Aken from 2021, if you can believe it, based on an old circle drawing algorithm of Marvin Minsky from 1972, and that's implemented online here. Now, the problem with this, from my point of view, is it's not scan converting a circle. It's just drawing pixels at roughly equal distances around a circle, and basically it'll tell you where to draw pixels and you have to find the nearest one. Now, that's not going to be very good. If you use too many pixels, let's say I change this to 400 here and restart it, basically when I go to draw these pixels, I'm going to end up with the same pixel multiple times before moving on to the next one. That's a bit wasteful. If I use too few pixels and restart it, then it's going to skip pixels. And so I basically would have to tune this on a per ellipse basis, and that just seems like too much work. So the other thing you might notice is it's not quite circular here, and so von Aken's algorithm improves on this, if I've understood correctly, by taking two competing versions with errors in opposite directions which cancel out. So very nice idea, and of course he also changes this circle algorithm into one for a general ellipse by basically doing some kind of transformation of the coordinates. The first idea I had was to take the pixels of an ellipse as I'm drawing them and just rotate them. And of course I need to do that in a very cheap way. Unfortunately, a lot of rotation algorithms end up with artifacts in the image. But there is a rotation algorithm that gets rid of the artifacts, and it's very cheap to implement. You start off with your image and you shear it horizontally, just like you are pushing a stack of paper to one side. And then you do the same thing in the vertical direction. Almost looks rotated at this point. And with one final horizontal shear, you can actually get a rotated image. The problem is it also changes the size of the image. It does get rid of all the gaps, but you need to do another scaling at the end to get it to the right size. But I figured it doesn't really matter how big it is because I can just adjust the size of the original ellipse and everything will be fine. So I went ahead and implemented this idea. Here's my code running in DOSBox, and we start off with an ordinary horizontal ellipse, which is much easier to implement. And I'm sure that a lot of people watching this video are probably saying to themselves, I'm pretty sure that my 8-bit computer could do diagonal ellipses. Well, here's what they were doing. Basically, they were just doing a shear of the ellipse, either a horizontal or vertical one, and this gives an alright looking result. It's not really a true ellipse, and if you wanted a proper rotation, you'd need to do the other shears and scaling. But it doesn't look terrible. Unfortunately, it's not pixel perfect. So finally I'll do the other shears and scaling, and this is what I end up with. And you can see that there are now gaps in the image and even pixels on top of one another. And this is what goes wrong when you take something that's scan converted for one orientation and try to use those same pixels in a different orientation. They're just not in the right place anymore. So this is obviously not going to be satisfactory. So let's look at de Silva's algorithm. This is the diagram he uses to describe it. He starts with the parameters for the equation of an ellipse, and there's a little bit of maths involved in that, which I won't go into. And then he divides the ellipse into 8 regions in exactly the same way as we did with the circle. You want an octant where you're always moving more horizontal than vertical, then one that's more vertical than horizontal, and so on. And the only thing you need to do this is the points where the crossovers between the regions occur. And so he uses some clever maths, well, who knew that calculus was actually useful for something, to actually explicitly compute these points. Unfortunately, you can't really do this easily with integer arithmetic. You need either fixed point or floating point arithmetic, so it gets really hairy to implement this. But it can be done. And once you have these points, then you can use pretty much the same algorithm that we've been using for circles and ellipses so far to draw these segments here. And he explains exactly how to do this. Of course, you're going to end up with a different set of parameters for each of these segments. And so it's a really long, complex algorithm, and the maths is pretty involved. Here's the pseudocode for his algorithm here, and you can see you start off with the 2 radii of an ellipse and a rotation angle. And it involves square roots, cosine and sine. So this is all pretty hard to do in assembly language. And there are other square roots down here. This is where the points are computed for the boundaries between the ellipses. And you can see it's all just given as a bunch of formulae. It doesn't really tell you how to implement this. There's a second page here, and this is where the actual points are drawn. And you can see it's very similar to what we were doing earlier. You have some constant values that get added to 2 variables, and those are used to update a decision variable every iteration of the loop. Now there are only 4 regions here rather than 8 because you can use a reflection because of two-way symmetry in the general ellipse, and so that saves you half the work. But this is very difficult to implement. In the end, I did manage to get it to work though. This is my first implementation of de Silva's algorithm. It's a little over 1,000 lines of assembly code, and it uses 32-bit values, 16 bits before the decimal point, 16 after. And immediately something goes wrong here. As I'm rotating my ellipse around, I stop getting ellipses all of a sudden for a while, and then it starts going back to ordinary ellipses again. It's also a little bit rough looking. It doesn't look completely smooth. The ellipses aren't quite round, but they're not too bad for the most part. There just seems to be something wrong for certain orientations of the ellipse. And it turns out that most of those issues were caused by errors in the actual algorithm itself. Some of the inequalities are actually incorrect and they're comparing against the wrong things. So that was the first thing that I had to correct. So after one hell of a lot of work, I finally got it to this point here. This will actually go all the way around without any errors, but unfortunately I discovered once I made the ellipses different sizes and different shapes, I was still running into issues.
And I scratched my head a lot about this, what I could actually do to fix it. And I realized that I was probably just running out of precision. I was working with these 32-bit values, and I only had 16 bits either side of the decimal point. Sometimes you need lots of bits below the decimal point, other times lots of bits above the decimal point. So it seemed like 32-bit values just weren't enough for this algorithm. Here's an example with a much narrower ellipse. And they look okay, I mean these are reasonable ellipses, but as it goes around you'll see it starts to miss points and it'll get really rough around the edges where it's at its maximum extent. And so something's not quite right here, and I had to spend a lot of effort trying to figure out what was actually going wrong here. Well, I eventually got to thinking about the precision issue and realised that if I'm running out of bits below the decimal point sometimes and other times above the decimal point, then this is really what floating point is designed to solve. It moves the decimal point about as needed and maximises the use of the number of bits that you have. The only problem is this machine doesn't have a floating point coprocessor. I don't even know if I have one to put in it. And besides that, I really wanted to have a program that would run on any 386 and didn't need a math coprocessor to be installed. So one way around this is to use a library that emulates floating point. And I could write one of those myself in assembly language. That would be a massive job. Or I could use the C programming language. So in the end, I realized that the algorithm is basically a whole bunch of setup that could be done in C, and then some actual code for drawing the pixels and doing the inner loops that could be done in assembly language. And so that's exactly what this version of the code does. I've let it run a little bit longer here, and you can see that it's still going just fine. In fact, this will go all the way through until the ellipses are basically circles. It just makes them wider and wider. You can see though that it's not quite pixel perfect. It's very close. But you can see some of the earlier ellipses just poking through at the edge here, and it's still a bit rough around the edges. But it's a vast improvement over the assembly language code that I had, which didn't look anything like this. So this is certainly one way to solve the problem, but in the end I was a bit dissatisfied with this because I'd set out to write an assembly language routine that could be put into, say, a library of graphical routines that other people could use. And I haven't really achieved that here. I've just written a C program for drawing ellipses. It's also incredibly slow. I don't think that can just be the floating point emulation, but it is definitely possible. There's only one way I'm going to find out whether this is going to go faster if I do the whole thing in assembly, and that is to write the whole thing in assembly language. But I didn't see any easy way to do that, so I started looking for another solution. Well, I got a tip online that there's a version of the Silva Ellipse algorithm in this book here. It's a very famous book, Computer Graphics by Foley, Feiner and Hughes. I had a copy of this when I was a kid, mainly for the photographs, I have to say. The rest of the text I tried to read, but a lot of it is about some very ancient graphics systems, which weren't even particularly relevant then, let alone now. But it is otherwise quite an interesting book, and in this there is indeed a section on scan converting ellipses. Now the problem is that this seems to be horizontal ellipses, which we already know all about. In fact, this is basically just the midpoint circle algorithm. But after a lot of searching, I eventually discovered there's a whole additional section on advanced algorithms toward the back of the book, and this is indeed a version for doing ellipses that are general or diagonal. Now the problem is that this is not De Silva's algorithm. This is for drawing a conic, and that's not what De Silva's algorithm does. So there was some speculation that maybe this was an adapted version of De Silva for general conics, but that's not the case. This is actually Chataway's algorithm from 1967, which I didn't actually realize at the time, but I decided to give it an implementation in C at least and see how it worked, and then I could evaluate whether it was worth doing this in assembly language. It seems fairly straightforward. Well, I did an implementation of this algorithm here, and as you can see, it really doesn't work very well at all. The other issue I faced is that about 3/4 of the cases for the algorithm are not recorded in the text. They're left as exercises. And so there's clearly something very, very wrong here. I read a little bit further in the text, and it basically explains that there are problems with this algorithm which need to be resolved, and those are left as exercises for the reader. It's not intended to be a completely working algorithm. By the way, it's 2 pages more than what I showed. I only showed the conic part, and there's also some additional pages for the ellipse part. So this is obviously a bit problematic, and in fact the issues that are unresolved in this algorithm are precisely the ones that De Silva does solve, and so it looks like I'm going back to the De Silva algorithm.
Well, I decided that I needed to just get serious with De Silva's algorithm. I mean, no one was going to solve this for me. I had to figure it out myself. And so I wrote a Julia program which takes the values that you pass into the algorithm, the 2 radii of the ellipse and the rotation angle, which I represent in a really strange way, and then print out all the values in floating point that get computed in that first page of the algorithm. And I started to notice some issues. These are the parameters for the equation of the ellipse itself, and this one D here can sometimes get really big. You can see this E7 here is engineering notation. It means multiplied by 10 to the power of 7, and so this means it's like negative 10 million. That's not going to fit in a 32-bit register if 16 bits are after the decimal place. So it seemed like I needed to do something to fix that. And then further down, I noticed these values K3 and K4 got very large. In fact, you actually square these in the algorithm, and already this value here wouldn't fit in a signed 16-bit value, and so there's going to be a major problem with those. And finally, you have to compute the values down here to start the algorithm off. These are the constants and variables that get used in the actual algorithm for printing the dots on the screen. And so these values are obviously way big as well. In fact, they get much bigger than this. And in the end, I decided I absolutely require 64-bit values for these. There's just no way around that. I need very high precision because these values are being changed every iteration, and they quickly accumulate errors, and then those values are being used to modify the decision variable, which is even more quickly accumulating errors. So I really had to use 64-bit values here, and for the rest I had to use a whole bunch of strategies, including shifting bits about and a bunch of different mathematical tricks to solve all the other precision issues, and it took weeks of work, but I finally got there, and this is the result.
In the interest of time, I've let this run for a while already. It started off with circles, and it's just getting narrower and narrower. And as you can see, the result is really quite fast. In fact, every half rotation here it's doing 804 ellipses, so it's certainly no slouch, and way better than the floating point code that we had earlier. So that must have been what was slowing it down. This is about 2,000 lines of assembly code, and I've tried it for many different sizes of ellipses, bigger and smaller ones than what you see here, and basically covered millions of ellipses in the end. And I had to find all the cases where things went wrong, and usually they were very narrow ellipses or very large ellipses, or ones at special angles like 45 degrees, where those values get really out of control. And so I had to find tricks to work around all those issues, which is why it took so much effort. But I'm really happy with the results, and I can now animate ellipses on a 32-bit machine. I don't think this would be practical on a 16-bit machine. You wouldn't want to be working with 64-bit values. You're really going to run out of registers in a major way, and basically the code would just be a real bugbear to write. It was already hard enough to do it on a 32-bit machine, I can tell you. So you will see one issue when we get toward the end. When the ellipses become very, very narrow, just a few pixels wide, we'll see a few additional pixels appear around the edge here where it oversteps. And this is basically a problem with all algorithms for scan converting ellipses. There's nothing we can do about that, but other than this, everything works absolutely beautifully. Well, I have to say I'm a bit exhausted after all of that, guys. There's a huge amount of programming for this episode. You might have also noticed there were some JavaScript animations for explaining how the algorithms work. And actually, I didn't write these myself. I actually got an AI to do it, specifically GPT-4. So hopefully you don't mind a little bit of AI-generated content. I'm not sure how well known it is generally, but this GPT-4 can actually write code in the major programming languages at least pretty well, and I pretty much just had to give it a description of what I wanted and then just make a few minor modifications at the end to fix some bugs, and away it went. So that saved a lot of effort on my part, but of course all the Ellipse code was definitely written by me. And I'm pretty happy with the result here. I had intended to do one additional animation at the end to show what you could actually do with all of this, but I guess that's something for a later episode. Time is ticking by, the video is pretty long already, and I've got to get to editing now. So thanks for watching as always, and I hope you enjoyed this look into scan converting general ellipses, and we'll see you in the next one. Bye!